Hello students, welcome to EPG Pathshala and I am Rima Gupta from University of Delhi. Today we are going to discuss about the module Electric and Magnetic Properties Part 8 and it is from the paper Ceramics. So students, let us see what we are going to learn in this module. So we will be discussing mainly two types of ceramics, that is piezoelectric ceramics and pyroelectric ceramics, and we will be discussing then their applications and properties. So let us discuss about the piezoelectric effect first. So the piezoelectric effect was discovered by Jacques and Pierre Curie in 1888. So the piezoelectric effect can be of direct piezoelectric effect or it can be inverse piezoelectric effect. So in direct piezoelectric effect, the ability of some materials to create an electric potential in response to applied mechanical stress is the piezoelectric effect. So the applied stress changes the polarization density within the material's volume, leading to the observed potential. As a requirement, only materials with non-centrosymmetric crystal structure can exhibit piezoelectric effect, and some of the commonly known piezoelectric materials are quartz, that is SiO2, zinc oxide, that is ZnO, polyvinyl fluoride, that is PVDF, lead zirconium titanate, that is PZT, and so on. So let us take the example where an oscillating applied stress on a piezoelectric material can give rise to the field which can be applied to an electrical load such as a bulb. So another example can be the charging of our phones or the mobile phones or any other device in your backpack while you walk. So you could not achieve the same while standing. So we can utilize that waste energy while walking into charging our phone using the piezoelectric effect. So students, one is the piezoelectric effect which we have discussed, and the second phenomena which we will be discussing is the pyroelectric effect. So in this case, the change in temperature results in stress. So let us discuss these two phenomena one by one. So in the introduction, we understand that the piezoelectric phenomena. So the piezoelectric materials can be categorized into two, the direct and indirect, or we can say as reverse or converse. So in direct piezoelectric effect, the direct effect occurs when applied stress to materials give rise to a change in the polarization density, which in turn can be detected as electric field or potential across the sample. Here, the polarization is directly proportional to the stress applied, which is described by the equation P is D into sigma, where P is the polarization, sigma is the applied stress, and D is the piezoelectric coefficient. Now, second is reverse or converse piezoelectric effect. So, the reverse is true when an applied field is applied to the material and as a result a strain is induced in it. It is expressed as epsilon is equal to D into E, where epsilon is the strain induced, D is the piezoelectric coefficient and E is the applied electric field. So the direct piezoelectric effect is used as the basis for force, pressure, vibration and acceleration sensors, while the converse effect is used as a basis for actuators and displacement devices. So the operation of piezoelectric materials. So students, you can see the diagram for the piezoelectric phenomena. So on the extreme left hand side, you can see that a compressive stress is applied which is resulting in the charge. So the polarization is also developed in a direction of applied stress. Similarly, in the bottom left hand corner, a polarization is given which result in strain induced. However, if we talk about, so the inverse effect as well as the direct effect is also shown in this figure of the slide. Poling of piezoelectric materials. As obvious from the previous slides, there are some piezoelectrics such as quartz which are not spontaneously polarized but get polarized upon the application of stress, while the ferroelectric, which are anyway piezoelectric in nature, are spontaneously polarized and show a change of polarization upon the application of stress. So the values of piezoelectric constants or coefficients for some materials are given in this table. For example, for quartz, the piezoelectric constant is 2.3 picometer per volt, whereas the piezoelectric constant for barium varies from 100 to 149 picometer per volts. But students, you can see that a maximum piezoelectric constant of 250 to 365 picometer per volt is also observed, and this is for lead zirconium titanate. So you can observe from this table that the level of strain generated is not so massive but is still important because of preciousness and reversibility of the effect. Most ferroelectrics have to be poled to be useful as piezoelectrics. In the unpoled virgin state of the material, the ferroelectric domains of single polarization direction are randomly distributed across the material, and in such a situation, the net polarization would be zero. So the application of stress to such a material would not achieve any change in the net polarization, therefore making it useless as a piezoelectric. So polling, that is the application of large electric field near Tc or just below Tc, that is the Curie's temperature, orients the domain along the field. And when the field is removed, the domain structure does not get back to the original condition, giving rise to a net polarization along a certain direction. Now, when a stress is applied to such a crystal, noticeable change in the polarization can be observed, and this is depicted by the figures showing on the right hand side. For example, before polling, where PR is 0, the domains are randomly oriented and the net polarization is 0. That is, resultant polarization is 0. But on the right hand side, after polling, when the resultant polarization is not 0, means the applied electric field has aligned the domains in its direction, hence resulting in some value of net polarization. So students, on the bottom corner of the figure, you can see that the polarization increases in one case and in another case the polarization decreases. So it completely depends upon the applied electric field. Some of the common materials which are piezoelectric are quartz, zinc oxide, that is ZnO, and perovskite structures. So in perovskite structures, some of the examples are barium titanate, that is BaTiO3, lead zirconium titanate, that is PbZrTiO3, bismuth ferrite BiFeO3, and some solid solutions. Some other oxides such as gallium iron oxide, that is GaFeO3 is also piezoelectric. However, other than oxides, there are some polymers which behave as piezoelectric materials, and one of the example is PVDF and Teflon. Now let us take some common piezoelectric materials and let us study about them. So the first material is barium titanate, that is BaTiO3. So this was the first piezoelectric material which was developed commercially for the applications in the generation and detection of acoustic and ultrasonic energy. We discussed its structure and transition in the previous section, and the transition temperature can be modified by chemical substitutions. So the barium substitution by Pb, that is lead, and calcium lowers the Tc of tetragonal to orthorhombic transitions. This has been used to control the piezoelectric properties around 0 degrees Celsius, which is very much important for underwater detection and echo sounding. The titanium substitution by zirconium or tin increases the transition temperature for both the tetragonal and orthorhombic rhombohedral transitions, enhances piezoelectric properties. The titanium substitution by 1 to 2 atomic percent CO3 plus leads to much reduced losses as high feels useful in ultrasonic applications. Care must be taken during processing to avoid the reduction of cobalt CO3 plus to CO2 plus, which occurs very easily. Now the next example is PZT. PZT is lead zirconium titanate. So PZT is one of the most used piezoelectric in a variety of applications due to its excellent properties and high enough transition temperatures. It has a perovskite structure with B sites randomly occupied by either isovalent titanium and zirconium ions. The typically used composition of zirconium and titanium is 50:50, which gives excellent properties. The reason for this is that this is close to morphotropic phase boundaries, and here at the morphotropic phase boundary, the rhombohedral and tetragonal structures coexist. As we know that PS vector is along 001 direction in the tetragonal phase and in 111 direction in rhombohedral phase. It permits material to be poled easily as there are quite very few polling directions available, making it a useful piezoelectric. The donor doping in PZT, such as lanthanum on lead side, reduces the concentration of oxygen vacancies. This in turn reduces the concentration of defect pairs, which otherwise impede the domain wall motion. This leads to noticeable increase in permittivity, dielectric losses, elastic compliance and coupling coefficients, and moreover reduction in the coercitivity. Now comes the applications of piezoelectric materials. So the piezoelectric ceramics are used in a variety of applications utilizing either direct or converse piezoelectric effect. So the first application is power generation, that is gas lighters. So the piezoelectric materials can ignite the gases by generating a spark through an electric current. This requires two piezoelectrics with opposite polarization states which are brought close to each other. So those polarization vectors are in the opposite direction. That is, the faces containing similar charges are together. The piezoelectric are replaced in a circuit with a spark gap. So the whole system of a gas lighter is shown in this figure. Now, the application of a mechanical stress or force will induce the change in the polarization. The force brings together these two pieces which then give rise to creation of charges. The charges flow from the end faces and the middle faces through the circuit, giving rise to a spark in a spark gap which can be used to ignite a gas. One must apply the force quickly, otherwise the voltage generated disappears because the charges leaks away through a piezoceramics across its surface and through the apparatus. So students, let us take another application of the piezoelectric materials. So it is in power transformers. A piezoelectric transformer works like an AC voltage multiplier. While conventional transformers utilize magnetic coupling between input and output, the piezoelectric transformer exploits the acoustic coupling utilizing inverse piezoelectric effect. So the piezo transformers can be quite compact high voltage sources. So an input smaller voltage across the thickness of a piezoceramic creates an alternating stress in the bar by the inverse piezoelectric effect. So this causes the bar to vibrate with a vibrational frequency chosen to be a resonant frequency of the block, and it is typically of the order of 100 kHz to 1 MHz in range. So this generates a higher output voltage in another sections of the bar by direct piezoelectric effect. So one can achieve step up ratios of more than 1000:1 using this technique. Now the second application which we are discussing in this module is piezoelectric sensors. Here typically pressure or force is used to create an electrical signal out to a piezoelectric material. For instance, in microphone, sound waves can deform the piezoelectric element by bending it and thus give a changing voltage. Similar principle can also be used for pickups, guitars and microphones. So other sensor applications are detection and generation of sonar waves to detect detonation in automotive engine by sampling the vibrations of the engine block, to detect the precise moment of fuel injection in an automotive engine, detection of acoustic emissions, microbalances, strain gauges, medical application using ultrasound waves, and kidney stone treatments are some of the sensor applications. So students, now let us discuss what is pyroelectrics and what are pyroelectric ceramics. So the pyroelectric materials possess spontaneous polarization along a unique crystallographic direction which may or may not be reversible by the changing polarity of applied field. If latter is true, then pyroelectric material is also ferroelectric. So if it is ferroelectric material too, then material can either be single crystalline state or a poled state. So pyroelectricity in itself is ability of materials to generate a voltage when they heated or cooled. It is temperature dependence of the spontaneous polarization in polar materials due to a minute changes in the atomic positions as a result of change in the temperature. So if the temperature is constant, then voltage gradually disappears due to leakage of charges through the material or air or apparatus. So the change in polarization on a sample surface can be measured as an induced current.
So this phenomena is shown in this figure.
Now the second category is pyroelectric ceramics. So the pyroelectricity was first observed by the Greek philosopher, that is Theophrastus, in 314 BC, who found that tourmaline attracted small pieces of straw and ash when it was heated. So first scientific description of this phenomena described by Louis Lambry in 1717. So in 1947, Linnaeus first related the phenomena to the electricity, although this was not proven until Franz Ulrich Theodor Apnes did so in 1756.
Now comes pyroelectric ceramics. So before moving that, let us discuss the history of pyroelectricity. Pyroelectricity was first observed by the Greek philosopher Theophrastus in 314 BC, who found that tourmaline attracted small pieces of straw and ash when it was heated. The first scientific description of this phenomena was described by Louis Lambry in 1717. After that, in 1747, Linnaeus first related the phenomena of electricity to the temperature effect, although this was not proven until Franz Ulrich Theodor Epinus did so in 1756. Now let us discuss the differences between pyroelectric and ferroelectric materials. Although both ferroelectric and pyroelectric materials must be non-centrosymmetric and polar, the essential difference lies between when an electric field is applied. While change in temperature below Curie's temperature leads to a creation of dipole along the polar axis by slight movement of atoms from their neutral positions, which is shown in this figure. Whereas a reverse electric field can be reverse the direction of polarization in a ferroelectric but not in pyroelectric material. However, when the material is heated above Curie's temperature, the atoms come back to their equilibrium position. Now let us discuss this figure in detail. So on the top left corner, you can see a pyroelectric and a FRIC. So the pyroelectric developed the spontaneous polarization below the Curie's temperature. This increases with temperature towards the Curie's point. However, unlike ferroelectrics, the polarization cannot be reversed by an electric field. The second case is shown on the bottom left corner, where if the temperature is raised back above the Curie's temperature, the polarization disappears again. Now, on the top right corner, you can see again a pyroelectric and a ferroelectric material, and below the Curie's temperature, both of them develop spontaneous polarization. Whereas when a reverse electric field is applied, the polarization reverses in the ferroelectric but not in pyroelectric materials. Pyroelectric coefficient. From the fundamental discussed in the previous, we can say that an electric field E is applied to a material and the total dielectric displacement, that is, charge per unit area of the plates on both the side of pyroelectric is D, and it is expressed as D is epsilon naught E plus PS plus P induced, which is equal to epsilon E plus PS. So here epsilon is permittivity of a pyroelectric material and PS is spontaneous polarization. Assuming that E is constant and differentiating the above equation with respect to temperature, it gives del D by del T is equal to del PS by del T plus E del epsilon by del T. Now defining generalized pyroelectric coefficient delta P, which is the change in polarization with temperature. So we can write delta P as del D by del T, which is equal to del PS by del T plus E del epsilon by del T. So del P is equal to P plus E del epsilon by del T, where P is defined as true pyroelectric coefficient and the last term in the equation is the temperature dependence of the permittivity of the material, which we can measure. Since polarization is a vector, so the pyroelectric coefficient is also a vector and has three components, which is defined by delta Pi is equal to Pi delta T. So the above equation neglects the change in dielectric constant with temperature and is valid only when such assumption is true. However, in practice, the electrodes collecting the charges are normal to the polar axis. We treat these quantities as scalars and the coefficient is usually negative because polarization decreases with the temperature. The behavior of polarization with temperature is dependent on the nature of transitions. Naturally, the pyroelectric coefficients, which are much larger in magnitude for second order transition than for the first order transition. Measurement of pyroelectric coefficient. One of the direct method of measurement of pyroelectric measurements is shown below. The circuit connecting a pyroelectric material which is held inside an oven with an amplifier and then measuring the pyro current. The pyroelectric coefficient is given as P is equal to IP divided by A of dt by dt, where IP is the pyro current and IP is equal to Is times 1 plus Rs by Rc, where Rs and Rc are the leakage current, or we can say these are the leakage resistance of the sample and input resistance of the amplifier respectively. Some of the common pyroelectric materials are tabulated in this table. So some of the materials are lithium tantalate single crystal, PMNPT, that is PMNPT, where P is lead, M is manganese, N is niobium, and T is titanium. The others are BST, triglycerine sulfate, and PVDF. So the structure, Curie's temperature, and pyroelectric coefficients are given in this table. So you can see that the pyroelectric coefficient for the BST is very much higher. Applications of pyroelectric materials. So some of the applications are in sensors relying on variations in ambient temperature, infrared or thermal imaging, power generation, burglar alarms, pollutant controls, and so on. So let us take one example, that is IR imaging. Just like we use visible light to make a photograph, infrared, that is IR radiation emitted by objects at different temperature, is focused onto a sensitive plate to create thermal image of the object. The atmospheric window typically used in IR imaging is from 8 to 14 micrometers, and coincidentally, the power radiated from a black body at 300 Kelvin peaks around 10 micrometer, making it a perfect match. The pyroelectric elements used in the devices are typically square plates with sides about a mm long and thickness of about 30 micrometers. Because entire scene are focused onto the plate in a thermal imaging, they have to be larger. Typically, squares of side of about 1 centimeter thickness are the same as for the simpler device.
So students, let us summarize what we have learned in this module. So students, First, we have talked about piezoelectric and then we have moved to pyroelectric materials. So, the important requirement was the non-centrosymmetry. So, the non-centrosymmetry is a requirement for both piezoelectric and pyroelectric materials. In piezoelectric materials, we have discussed that all the piezoelectric materials are non-centrosymmetric materials and there can be two effects, that is direct or indirect. So one is direct piezoelectric effect and the another is indirect piezoelectric effect. So both these effects make one use coupling between the stress and the electric field. So in piezoelectric effect, we have read that when we apply some electric field, the stress is generated, or when we apply stress, the electric field is generated. Then we have discussed about the applications of piezoelectric materials or the piezoelectric effect in various applications like charging phone or energy harvesting and so on. After that, we have moved on to pyroelectric materials. So, those with a unique polar axis are pyroelectric materials, and in them, the polarization is along the polar axis. So, these materials are useful for various sensors and actuators applications. So, students, now from this module, you will be able to answer the questions related to piezoelectric and pyroelectric ceramics. Thank you.